In the morning, a cloud is born in the Arizona mountains. It is almost full grown, 3 miles from base to top. Nearby, another cloud also approaches maturity. By early afternoon, the first cloud has begun to die. But the second has exploded into wild growth. Churned by violent updrafts, it towers over all. It spills rain on the peaks and valleys. 2 clouds that look alike, but vastly different in development and amount of rainfall. What happens in the misty caverns of a cloud? More important, can these scientists fly into a cloud and make it give rain to a needy earth when it would not naturally do so? Weather is a global phenomenon. To study it, and thus hopefully learn to control it, scientists sometimes take the long view from a satellite in a fixed position above the Earth.
Ignition! Main stage! 4, 3, 2, 1, 0.
Repeating time-lapse film of the Earth, taken from a stationary satellite, reveals huge masses of air pushing out from the poles, colliding with warm, moist air from above tropical oceans. Where they meet, at a front, vast cloud decks form. Along the fronts, storms are born, and rain and snow. Away from the front, a different kind of cloud grows, the cumulus, shaped by local influences. Only recently have scientists begun to understand the dynamics of these small clouds, the ways in which cloud droplets grow, and the composition of the invisible particles that trigger rainfall. Although we sometimes cannot see it, there is always moisture in the air. It floats across the hills and valleys as vapor. Clouds form when it turns to tiny droplets and ice crystals. To make rain or snow, the droplets must grow large enough to fall to Earth, a major area of research in weather modification. This radiosonde measures the pressure of the atmosphere as it is borne aloft by balloon and radios back the data. The chart reveals that on this day, the pressure at ground level is about 29 inches of mercury, is only about 27 inches at an altitude of 2,000 feet, and 25 inches 1 mile up. The higher the balloon goes, the less dense the air. Such air, heavy in the lower layers and light in the upper layers, rests comfortably. It is stable. The airflow over the city of Denver, as shown with a model, demonstrates such stability. This low-speed wind tunnel at Colorado State University has temperature controls that can cool the slab on which the model rests, cooling the air above it and making it dense in the lower layers, or stable. Smoke flows smoothly in stable air. But suppose we turn on the heat and warm the floor of the tunnel, just as the sun warms the Earth. Now the air, warmed from below, becomes unstable. It rises, creating strong updrafts. Soaring birds easily ride the updrafts in unstable air. Some rising columns of air are so powerful they can support a sailplane. As air rises, it expands and cools, the way air cools when let out of a tire. But cool air cannot hold so much moisture. It becomes saturated, and some of the moisture condenses out as tiny droplets. Condensation is triggered in other ways. When air flowing along the ground reaches a mountain slope, it is forced to rise. It expands and cools. The air becomes saturated, and moisture condenses out. Researchers with the Atmospheric Sciences Research Center traveled to Yellowstone National Park to study another element, a crucial one, in the conversion of water vapor to cloud droplets. They chose the park because mountains protect it from industrial pollution, and because the geysers tend to scrub the air, leaving it relatively pure for their experiment. Vapor can supersaturate the air, yet not condense out until there are nuclei to condense on. In the presence of chemical smoke particles, cloud droplets quickly form. Condensation can be demonstrated in the laboratory with salt crystals on a spider web as nuclei. As the droplet grows, the salt solution becomes weaker, losing its attraction for water molecules. For that reason and others, the droplets reach a maximum size. This geyser plume demonstrates a further cloud mechanism. First, vapor condenses to form droplets. The droplets cool to very low temperatures, but they do not freeze. They remain liquid. In this state, water is called supercooled. In this experiment, silver iodide is burned, producing billions of tiny particles, or nuclei. When particle and water meet, ice crystals form. The tiny crystals sometimes combine and fall out like snowflakes. Scientists at the National Center for Atmospheric Research are conducting a full-scale search for nuclei in the atmosphere. They scoop up the tiny particles and trap them on microscope slides. The plane flies at high and low altitudes over both desert and ocean areas. In the laboratory, the microscope slides are photographed and the particles counted by size. The sample in this photomicrograph was collected at an altitude of 50 feet over the ocean near Santa Barbara. The particles, a few thousandths of an inch, are mostly sea salt, good nuclei for vapor to form droplets on. At 1,700 feet over the ocean, there are fewer particles. These small bits of land material make good nuclei for supercooled droplets to form ice crystals on. This sample, taken over Death Valley at 3,000 feet, apparently contains biological material, perhaps from plants or trees. Over the oceans, there are generally fewer than 100 particles per cubic centimeter of air. There are more than 1 million particles per cubic centimeter in the air we breathe in large cities. Early results indicate that a good percentage of the particles in the air around us can trigger condensation. But the big questions still stump the scientists. What are the particles made of? Where do they come from? Which kinds could be used for making rain? Cloud droplets, then, form under special conditions. If the air is saturated, and if there are nuclei to form on. But cloud droplets are so incredibly small, like the point of a needle, that they do not fall. To become raindrops that will fall to Earth, they must grow 1,000,000 times in volume. In other words, it takes 1,000,000 droplets to make one raindrop. Scientists at the National Center for Atmospheric Research are studying the ways in which droplets grow. They produce two streams of droplets. The droplets fall at the rate of 600 pairs per second, but their motion is apparently slowed down when viewed in stroboscopic light. As filmed through a microscope, the droplets actually collide in midair, but do not coalesce. Apparently, the thin layer of air between them prevents them from combining. But since the days of Benjamin Franklin, meteorologists have known that clouds are electrically charged. What happens to these experimental droplets if they are given an electric charge as they pass through the needles? Charged droplets coalesce more effectively, producing larger droplets that may fall to the ground. But scientists do not know how to control cloud electrification to increase rainfall. At Colorado State University, researchers are studying the interaction of supercooled droplets and ice crystals. In this chamber, the temperature can be lowered to 0 and below. Steam is fed in, producing a cloud of supercooled droplets, just like the droplets in the geyser at Yellowstone. This burner produces billions of silver iodide particles. Injected into the chamber, they serve as ice crystal nuclei for the droplets, just as the burning flare produced particles in the Yellowstone experiment. And ice crystals form. Through the microscope, the researchers study the crystals, typical stellar formations, and hexagonal plates that form at certain temperatures. But more important for making rain and snow, the ice crystals grow large at the expense of the water droplets. If the process continues in nature as in the chamber, the crystals may grow large enough to fall to Earth. Research conducted by Dr. John Hallett, now at Desert Research Institute, shows how ice crystals grow layer by layer. The nucleus for these crystals was copper sulfate, also similar in structure to ice. The changing colors in this kind of photography reveal growth. In clouds containing the correct number and distribution of droplets, crystals can grow very rapidly. But how can scientists study these complex processes in nature? How can they get inside a cloud to collect data without disturbing the delicate balance between temperature, pressure, and humidity? One technique has been developed at Colorado State University. High atop the Continental Divide, this team is studying orographic storms, mountain-borne groups of clouds. To place their instruments inside the clouds, they use a kite, which is similar to an airplane wing. This air sampler can be sent directly into the cloud, then triggered from the ground to capture a small parcel of air. Later, the sampler is removed and rushed to the laboratory. Here, the air is forced into a chamber under pressure. When the air pressure in the chamber is decreased, the temperature drops, just as it does in nature, and the moisture in the kite sample freezes into crystals on the nuclei. These fall into a sugar solution and grow into much larger crystals, which can be easily counted. Researchers also capture ice crystals at various altitudes. The crystals enter this replicator and become embedded on soft film. Later, the crystal image is magnified as much as 75 times. By observing the shape of the flake, scientists can tell at what temperature, and thus at what altitude in the cloud, the crystal was born. This plate with extensions was found at about 12 degrees above zero, while this bullet was caught high in the atmosphere at a temperature of 22 degrees below zero. This long hollow column was collected at 16 above. The larger the crystal, no matter what the shape, the more water there is in the cloud. Researchers at Desert Research Institute are trying to quantify this relation between temperature and crystal growth. The temperature in this chamber runs from 60 degrees above zero at the top to 70 degrees below zero at the bottom. Water flows down a fiber, forming a warm cloud at the top, a supercooled cloud in the middle, and ice crystals in the coldest part. The crystals vary with the changing temperature along the fiber, a difference of 1 degree, sometimes changing the crystal dramatically. But can scientists actually make it rain? Dr. Vincent Schaefer of Atmospheric Sciences Research Center discovered one method. In an experiment in 1946, shown in these historic photographs, he dumped 6 pounds of dry ice into this supercooled cloud from an airplane. In 5 minutes, the cloud had begun to dissipate as snow. 10 minutes later, most of the cloud had turned to snow. But since there is so little moisture in this kind of cloud, much of it re-evaporated before reaching the ground. The experiment raised a storm of controversy. So the group took off again in April 1947 and seeded this huge cloud deck, punching a giant hole through it as the snow precipitated out. But non-believers said that snow might well have fallen naturally from this cloud at that time. So the group cut a very unnatural racetrack pattern in their next cloud. These researchers are about to seed a cumulus cloud with silver iodide particles, providing extra freezing nuclei for crystals to form and grow on. The cumulus cloud on the right will be the experimental cloud. The one on the left, the control. Their attempt is part of an experiment conducted each summer for the Bureau of Reclamation near Flagstaff, Arizona.
We have the ESTA pictures here from last night. Shows the cold front moving across the central part of the United States and with trailing into the lower mountain states. There's this trough still hanging out in the Pacific and the trough over southern part of Canada moving in. Looking down now at the local area, the best we can tell, the low-level front is hanging right along the rim this morning. The upper level flow is very strong. It's coming in at 30 to 40 knots. Winslow's even reporting 60 knots. This means that the convection will pump the moisture up, but then it will be sheared off very rapidly to the north. And during the late part of the day, we'll get this tremendous anvil cover, cirrus cover like we had yesterday. For operations today, the cloud bases will be at about 11,500, freezing level at 14,000. We expect the -10 to be at about 19,500 to 20,000, and tops for the early clouds at about 22,000 feet. The seeding activity will involve cumulus that are more or less stabilized by this inversion that occurs at about 18,000 feet. So with proper seeding, the release of the latent heat will cause these clouds to grow, and the growth would be something the order of 10 to 12,000 feet. The aircraft operation will be the Cessna 180 working at cloud base and doing the seeding. The Aztec will be working at -10 or around 19,000 feet. He will be penetrating back and forth, making measurements of the ice crystal concentrations or supercooled water. Takeoff times again will be for the Aztec about 9:45 to 1000. The 180 will be off at 1000, 10:15. We'll meet over Sunset Crater, sounding to 24,000 feet by the Aztec. Then he'll return back down to his working altitude at 19.5. We will probably take the Sunset area as our first area because we're running tight. We need to get the first clouds in quick before we get the anvils over the area. That's about it, unless there's some questions.
First off the ground is the research plane. It will spiral down through the cloud, measuring the electric field and mapping the distribution of nuclei and supercooled droplets at different altitudes. This plane will seed the cloud from below, so the updrafts can carry the particles up inside to create ice crystals and hopefully rain. A computer prediction process has estimated 2 inches of rain if the seeding is successful. Radar operators will track the plane and measure the cloud.
All right, Liz, acquire the aircraft.
Acquiring airplane. On track.
On track. Got 2, here we have you on track.
Roger.
All right. Aircraft is proceeding toward the seeding area. Prepare to drop the aircraft on the event.
Dropping track.
That's vertical scan.
Beginning vertical scan.
The radar echo from the water in the cloud indicates cloud top and cloud base.
Have first echo.
We have a first echo out.
well now.
The Aztec probes the seeded cloud. In this experiment, the control cloud produced more rain than the experimental cloud, although each produced the amount predicted for it. A recent study of cloud seeding experiments shows that rainfall from cumulus clouds can be increased about 10 to 20%. In winter storms, precipitation increases of about 10% apparently result from seeding. But seeding individual clouds and local storms is a far cry from modifying the weather systems that cover half a continent. A suitable object of tomorrow's research.